In episode 44 of the SOC Level 2 training series, we are going to go through the advanced static analysis room that is inside of the malware analysis module of TryHackMe. And this is the build up, right? So we did basic static analysis, and then we did some exercises that we can use, or that we used everything that we've learned so far for malware analysis, looking at the various tools that we used, etc. And now we're going to go through advanced static analysis, which is, as the name implies, the advanced strategies for doing static analysis, meaning you're not running the malware yet, because we're going to get into dynamic analysis in the very next video, or maybe the video after that one, because I think the next video is going to be the challenge questions for static analysis, for the advanced static analysis. So we're going to go into dynamic analysis where we actually run the malware, but in static analysis, we are still analyzing source code and the contents of the malware without actually running it. And the overview of this content is obviously the intro malware analysis overview, connecting to the virtual machine, which is going to be our controlled environment, Ghidra, a quick review for that, identifying C code constructs in assembly, the overview of Windows API calls, common APIs used by malware, process hollowing, and analyzing process hollowing. And then finally, we have the conclusion where we'll review everything. I'll give you some final thoughts, some final notes, and then we'll wrap it up, and then you'll be dismissed for the day. So this is a subscriber-only room that's available inside of TryHackMe. However, the virtual machines that we're going to end up using are available for anybody who just wants to get access to those virtual machines. I think in this particular case, it's just giving us a virtual machine specifically, and it might be a Windows machine. Yeah, it is a Windows machine because it says that we can RDP into it, and RDP is pretty proprietary. It's native to Windows machines. But you can technically use your own Windows machine to go through exercises like this, because you can always get the tools that we're going to be using to do the exercises yourself. I just wouldn't recommend that you download and run malware on your own computer. So just please be careful with that specific piece. It's like a very small detail, but it's a really, really important detail. So don't download malware just because you want to try the tools, okay? It's very, very important that you understand that. Apart from that, everything else you should be able to get access to, because we're only going to be using open source tools to do everything that we're going to do in this particular video. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. Now, without further ado, let us dive into advanced static analysis. In the basic analysis video, the basic static analysis video, which was the second video prior to this one. So if you go back one, that was the exercise that we did for practicals, and all we were just answering questions and doing an investigation. The video prior to that one, so I want to say it's episode 42, that was the basic static analysis video. And we looked at characteristics like strings inside of the content of the malware, hashes, import functions, and other key information that was inside of the header, the portable executable header. And that was pretty much it, right, to get an idea of the malware. And in advanced analysis, we're actually going to be looking at the disassembled code and analyzing the assembly instructions to understand the malware's core functionality in a better way. You don't need to necessarily know code, okay? So I just want you to understand that. For a lot of people, including myself, coding is not this really deep skill that we've developed as we got into cybersecurity, and we're kind of learning coding as we go along. And for me, before I got into cybersecurity, the only coding languages that I really understood were HTML, because I used to do web development, and then a little bit of Python because I created some very basic automations using Selenium, which were like web browser automations. And that was basically it. That was the furthest extent of my coding knowledge. I knew nothing about bash scripting. I knew nothing about PHP. I knew nothing about C or C+. or C++, any of those things. So just want to let you know that you don't need to know coding, okay? That's just the key thing. You're going to learn as you go, and I'm going to do my very best to explain the code, and then I will be using tools like the various AIs that are available so that we can get even a better understanding of the code if we need to understand the code. So just want to let you know that. Advanced static analysis is a technique used to analyze the code and structure of malware without executing it, right? So we're still static. And this can help us identify the malware's behavior and weaknesses and develop signatures for antivirus software to detect it. By analyzing the code and structure of the malware, we can get better understanding of how it works and develop new techniques for defending against it. So this is what happens typically, right? So you have the code, it gets compiled, right? And it becomes an executable. And then when you disassemble it or decompile it, you get the actual code itself, the assembly code itself. And it's not, the assembly code, from what I understand, is not the raw code, right? So it gets compiled, it gets disassembled, and it becomes assembly code. So this room is designed to help you acquire the knowledge needed to reverse engineer malware effectively. And we're going to learn assembly instructions more systematically, enabling us to identify important functions more easily instead of getting carried away by each instruction. So that's the key element here, right? So again, as this sentence just implies right here, you just want to be able to identify the important functions instead of getting carried away by each line of code, which can definitely be overwhelming because there are going to be hundreds of lines of code depending on the complexity of the malware. Some of the topics are how advanced static analysis is performed, exploring Ghidra's disassembler functions, and I think this is technically supposed to be pronounced Ghidra, and not very many languages have the G sound. It's very different from the R sound that is in French. Ghidra, from what I understand, or the G sound, I think is like 2 or 3 languages that actually have that sound. And Persian, Farsi, is one of them. That's the only reason why I know how to pronounce it. But I think for the most part, most people just say Ghidra. So just keep that in mind. That was my opportunity to flex my language skills a little bit. Understanding and identifying different C constructs in an assembly. And these are the prerequisites, right? So this is actually where we're going to be referencing the architecture videos that we did a little bit, which are a part of malware analysis. So it would be in the last series of videos, and you can see the title. So x86 architecture and assembly are actually in the title of the videos, and then basic static analysis, which we've already done as well. So those are all of the prerequisites. If you have not gone through them, I would encourage you to go through them. These two are very detail oriented. If you've never seen architecture or assembly, you will, for the most part, I think you will be overwhelmed. So I'm just going to set that precedent for you. It's not crazy, right? So it's not like you're not going to be looking absolute nuanced details of everything, but there are some pretty fine details. For example, learning how binary code translates to ASCII or Unicode, etc. Okay, here we go. Let's go on. This is probably as good a time as any to do another overview of what malware analysis is and the different elements or the different steps, phases inside of malware analysis. So we're going to be examining malicious software, also known as malware, to understand how it works and identify the capabilities, behavior, and potential impact. There are 4 steps in this. There's basic static analysis, basic dynamic analysis, then there's advanced static analysis and advanced dynamic analysis. We haven't done any dynamic analysis yet, so we've been so far just talking about static analysis. Basic static analysis is to understand the malware's structure and behavior without executing it, and we would be looking at code, file headers, and other static properties. Basic dynamic analysis is to observe the behavior during execution in a controlled environment. So controlled environment is the key phrase here, also known as a sandbox or some kind of a dedicated virtual machine or something. So hopefully it will not get onto your host machine. A lot of malware, complex, sophisticated malware, have elements in place, functions inside of it that can detect virtual machines and evade running inside of a virtual machine. So if you actually run it inside a virtual machine, then if it's a complicated or like a sophisticated malware, it actually won't do the malicious activities because it's detecting that it's being run inside of a virtual machine, And that's, where malware authors get really clever with these kinds of things, because they know that as a part of analysis, security engineers and security analysts are going to be running the malware in a virtual machine in a controlled environment. So, just kind of pointing that out for you. Running it in a sandbox or a virtual machine and then monitoring the activity, network traffic, and process behavior, that's all dynamic analysis. When we get to advanced dynamic analysis, is where to uncover more complex and invasive malware behavior using advanced monitoring techniques. This involves using more sophisticated sandboxes and monitoring tools to capture the malware behavior. And advanced static analysis aims to uncover hidden or obfuscated code, also known as disguised code or filtered code, so to speak, and the functionality within the malware. It involves using more advanced techniques to analyze the malware's code, such as de-obfuscation and code emulation. How advanced static analysis is performed is essentially to discover the capabilities and identify the attack vectors and determine the evasion techniques. And to do this, we use disassemblers like IDA Pro, Binary Ninja, and Radar E2 maybe. I think it's not Radar. I think it's Radar E2. These disassemblers allow the analyst to explore the malware's code and identify its functions and data structures. The steps involved in performing advanced static analysis are: identify the entry point of the malware and the system calls that it makes, identify the malware's code sections and analyze them using available tools like debuggers and hex editors, analyze the malware's control flow graph to identify the execution path, and trace the malware's dynamic behavior by analyzing the system calls it makes during execution, and finally, use the above information to understand the evasion techniques and the potential damage that the malware can cause. So, does advanced static analysis require executing the malware in a controlled environment? And that is nay, because that would be a part of dynamic analysis. So if you think about running it, think about dynamic, right? Dynamic requires running. Static, you're not running it. And that's the only question that we have. So let's talk about connecting to our virtual machine. And I'm just going to click that and start the machine. As per usual, if you've never connected to a virtual machine inside of TryHackMe, there are two options to do it. You can run it inside of the browser, which is what I usually default to, and it'll open up in split view. Technically, sometimes the virtual machines are target machines that we would use inside of hacking exercises. And so if you do that, you would also need to launch the attack box as well. But usually inside of defensive exercises or investigations like this one, as soon as you click start machine, the window kind of splits in half, as you just saw. And I had to shrink it because I'm super zoomed in. I'm at 300% view on my browser because I want to make it easy for you to read the content as I read along. But usually I will open it up in a brand new window so that we can look at the full machine as if we're literally inside of the computer. You can also access it via RDP or SSH. Now, when they say RDP, it just automatically implies that we're going to be using a Windows machine. If they say SSH, that means we're using a Linux machine. If you do use RDP, then you would just use whatever the IP address is that's assigned to you. Now, this IP address is going to be taken down as soon as I end this recording. I always say this because sometimes people get, wise ideas and they think that they can go ahead and try to do pen testing against these IP addresses. These IP addresses, number one, are fully protected. They're inside of the virtual private network of TryHackMe. To even be able to get access to them, you need to actually be connected to the VPN of TryHackMe or via VPN to TryHackMe servers, and then you'll be able to run kind of exercises towards that. Apart from that, they're completely blocked off, and they are taken down by the time that the video is finished recording. So just keep that piece in mind. But you can remote desktop into it, and these would be the credentials that you would end up using. So I have successfully launched the VM, and let's see how many files are present in the code constructs folder on our desktop. So here it is. This is the Windows machine. It looks like a Flare VM machine. So this is the VM emblem, the VM logo for Flare VM. This is not my favorite installation of Windows. I'm just going to be honest about this because it tends to kind of run slow, but hopefully it will be fine. So we have a total of 5 files inside of the code constructs folder. So we'll just enter that, and we will now move on to Ghidra or Ghidra. There are many disassemblers in the world of security. We have Cutter, we have Radar, E2, Ghidra, IDA Pro, and they can all disassemble malware. We're going to use Ghidra because it's free and it's open source and it has a lot of features that can be utilized to get proficient in reverse engineering. And the idea is to get comfortable with the main usage of a disassembler and then use that knowledge to use any kind of disassembler because for the most part, they will be serving the same function. It's in a software in reverse engineering that allows us to analyze compiled code and understand the functionality. And it's designed to help analysts, developers understand the workings of the software, right? So how does the software work? By providing a platform to decompile, disassemble, and debug binaries. I absolutely love the logo because I am obsessed with dragons. It's one of the things that I became even more obsessed with as I got into ethical hacking and cybersecurity because one of the logos for Kali Linux is this gorgeous dragon that they have. So this is just a different dragon. It's not the Kali Linux dragon. Let's not get confused here. But the Kali Linux logo, at least the most recent versions, are also a beautiful, beautiful dragon logo. Okay, so these are the features of Ghidra, okay? We have the decompilation that it can decompile binaries into readable C code, making it easier for developers to understand how it works. Disassembly, that it can disassemble binaries into assembly languages, allowing us to examine the low-level operations of the code. Debugging, that allows users to step through code and examine the behavior. And analysis, to help us automatically identify functions, variables, and other code to help us understand the structure of the code. When you launch it, this is kind of what it looks like. And I've already launched it, so this is like the full view of, or like the large view of what it is. And then you kind of just open the file, right? So you can first create a project, and all of these things is, I'm just kind of like breeze through this because we're actually going to apply these steps. So you open it up, you create a new project by doing new project. You select a non-shared project so that you're just using it for yourself. You can also do shared project if you want to share it with your coworkers. You name the project and set the directory, or you can just leave the default path for the directory. And then you import the malware executable. So this is where we actually bring in the executable that we want to analyze. And in this particular case, it's the Hello World executable that is on the desktop, and it's actually on this desktop right here as well. That's the executable right there. So you import it, you click OK, and it basically starts running, right? And so it'll show the summary of the program as we see right here, the file name, the read-only, if it is read-only or not, the compiler ID, processor, the number of bytes, the number of instructions, etc. And we can double click on this to open it in the code browser, right? So this is what we have here, where we actually get the import results summary. And then if you double click on it inside of this piece right here, I believe, when we double click on this, it'll actually go inside of the code browser that we have. And when asked to analyze the executable, you want to click on yes. So that's a big piece. The next window that will appear shows us various analysis options. We can check or uncheck them based on the needs. And these are the various options that we have. And I'm not going to read through all of them. You can pause the video if you want to zoom in on it and just read through what they are. But depending on what your use case is and the information that you're trying to find and your skill level, I would say, you would use a variety of these different analysis options. It will take some time to analyze. The bar in the bottom will show the progress. Wait until it hits 100%. Okay. There are many options that we can aid in the analysis. The default layout is as such. So they're going to give us descriptions for this. And so we're going to start like this, right? So we have 1, 2, 3 on the left side pane. And then we have 4, which is the central portion, 5, the right portion right here, and then 6, which is just a toolbar at the very top. So program trees shows the sections of the program. We can click on different sections to see the content within each section. Dissecting PE headers room, which was one of the videos 2-3 videos ago. It explained the headers and the PE sections in depth, and we used PE tree for the most part to do that. Symbol tree contains important sections like imports, exports, and functions. Each of these provide a wealth of information. The imports contains information about the libraries being imported by the program. Clicking on each one of them shows the assembly code that uses that API. Export contains API or functions that are being exported by the program, and this is useful when we're trying to analyze a dynamic link library because it'll show all the functions that the DLL contains, and then there are the functions themselves that you can find inside the code that will show us the disassembled code of that function, and it contains the entry function. Clicking on entry will take us to the start of the program that we're analyzing, essentially where the activity starts, right? So that's the entry of the functions themselves or the program itself. And the stuff with generic names like fun, virtual address are the ones that Ghidra does not give any names to because I guess they're generic. Then you have the data type manager, which is still on the left side. This shows us the various data types found in the program. Then we have the central portion, this large portion in the middle right here. And these are the listings. So this shows the disassembled code of the binary, which includes the virtual address, opcode, assembly instruction like push, pop, add, XOR, etc., operands, and comments. Then we have the decompiled, which was on the right side, that translates the assembly code into a pseudo C code. It's very important to look at during analysis because it gives us an understanding of the assembly code, the toolbar at the very, very top, and that one's fairly self-explanatory. The graph view in the toolbar is an important option because it allows us to see the graph view of the disassembly. And so I guess this is the graph view, kind of. I don't really associate this visual with a graph. I feel like a graph view would be, like a graph. This doesn't really seem like a graph to me. Oh, maybe it's these arrows that they're talking about. Maybe that's what they're referring to. Okay, I guess that's a graph view. Whatever. Memory map option shows the memory mapping of the program. And so if we click on memory map right here, it gives us the memory map and the headers. And these are also things that we, inside of dissecting PE headers, we talked about these various types of headers as well. And the various elements, read, write, execute, whether or not it's volatile data, meaning if it's inside the RAM, etc. And the navigation tool shows us different options to navigate through the actual code itself, which I guess is what they're talking about, this specific element right here maybe. We can explore strings, so search for strings, and click search will give us the strings that Ghidra finds within the program. It can contain very juicy information because strings are actually very useful, as we went through when we were doing the basic static analysis video. And these are a bunch of different strings. So you have the location of them, the label of the string, the actual code unit that they belong to, the string view itself, and I guess the contents inside of the string. So this is technically the contents inside of the string. And analyzing our actual executable, so this is what we're going to be looking at in this particular case. I would say that doing it in in Ghidra, analyzing this specific executable is what we're looking at right here, because there is a separate executable inside of our code constructs that's also called hello world, but it's hello_world. It's not the same as this, I don't think. So I'm just going to say that there are two different executables. To define the assembly code for this, we'll double click on the .text in the program tree section. It will take us to the disassembled code section, and we're going to scroll through it until you see the call for the message box that will display hello world string in the decompile section, and we can see the translated pseudo C code of the function. So the disassembled section shows us how the arguments are being pushed, followed by the message box A, responsible for the message box display, which is what we would see most likely right here. So let me see if I can kind of zoom in a little bit. So we have text. If we click on text, it'll take us to the text section. In this particular case, we have the push functions in the center right here. And then there's a message box A that's highlighted in yellow right here that has the message hello world. And that's kind of the function of the executable, I guess, right? So we can explore the features by examining the simple hello world. In the next task, we're going to do different C constructs. It's trivial to note that the malware's author may have packed or used obfuscation or anti-VM, anti-AV detection techniques, anti-virtual machine, anti-antivirus to make the analysis harder. These techniques will be discussed in future videos. So how many function calls are present in the exports section? So let's see, this is for, what is it? For the hello world executable, I believe. So this is what they're talking about. And so if we want to look at that, I guess what would happen is that, I don't know if it's going to be inside of the screenshots that we have over here. I feel like it's not. So let's see if it is in this case in the exports section. What is that? Export section is inside of the symbol tree, which is this piece right here. And it doesn't show us the answer. So we actually do have to analyze our code here. So let's go ahead and create a new project. And from here, we're just going to be a non-shared project. We're going to click next, and I'll just name it Hello World. My keyboard went to sleep again, so Hello World. There we go. That's going to be the project. And then I'll even do project just so I don't confuse it. And then we're going to finish it. And then there we go. So now we have the Hello World project. And now we're going to go here, and then we're going to import a file inside of our project. And that will be the one on the desktop, which is the Hello World executable. And we're going to import the executable. I could have also dragged and dropped it. And then now we have this various stuff as well that was previously available. And I'm not going to change any of this. I'm just going to click OK on this. And it will now start to import it. And now we're going to wait until this hits 100%, which it did fairly quickly. This is our summary, which is great. The number of functions is actually right on the summary. So it says 16. I wonder what the question was. I think it asks for the number of functions, right? So how many function calls are present in the export section? Okay, that's definitely not the answer that we're looking for. So we want the function calls in the export section. So I will go ahead and double click on this, and it will now load and do all the analysis and everything. And hopefully it will not take too long. It did not take too long. Great. How would you like to analyze it? I do want to analyze it. I'm just going to keep all of the basic default options. And then I want to say, oh, you can't really see it because it's like right below here. But there is a progress bar at the bottom that we're waiting to hit 100%. So maybe I can kind of drag this down a little bit and minimize it, or maybe if we expanded it, let's see if I expanded it fully. Yeah, okay, you can see the progress bar at the bottom right here. So it's analyzing the thing, and it goes to 100% multiple times. So I'm guessing it's doing multiple sections at 100%. So we're just going to wait for that to be fully done and stop running because it's still running. And when that happens, we will then go ahead and see how many functions are inside of the exports section. Okay, cool. So that took, I want to say like maybe 2 minutes. It wasn't really that bad. Now we can click on the exports file right here, or the exports location, and maybe even expand it. And we have entry, and then expand that, and maybe not. There we go. Okay, there we go. So we have the entry point for the exports. I want to say that's what it is, right? That's what we're asking for. It says how many function calls are present in the export section. Is it 1? Okay, I guess it is 1. The function call is entry. That's basically it. There's literally 1 item inside of this exports folder. So, okay, that makes... All right. For a second, I was like, that can't be just 1, but it is just 1. What is the only API call found in the user32 DLL under the imports section? So we are going to click on imports, and we're going to just expand it. And then under user32, there is 1, and it's message box A. That's the only one here. So we'll do message box A. How many times can the hello world string be found in the search for strings utility? So we're going to go up here, click on search, and we're going to search for strings. And what we're going to do is we're going to search for what is the full string? Where is it? Where do I actually type this in? I guess, is it here? No, it can't be. That's the word model. Require minimum lex, and okay. What am I searching for, buddy? Oh, maybe that's what it is. So inside of all of these things, now we can try to find hello world inside all of these things, maybe. So let's do I'll do a select all here, and then let me see if I can do Control F inside of this environment. It doesn't seem to allow me to do it, but if I click on this little search icon at the top, Maybe that's what it is. So show undefined strings. Let me see. Okay, the search function is actually at the bottom right here. So this is the filter where we actually look at it. So first we look for all the strings, we pull all the strings, and then from there we will find whatever we want by doing hello world. It does only show me one, so I'm gonna go ahead and do the search for these strings one more time because there is this minimum length and alignment and all those things. I just wanted to make sure. So I thought this was maximum length and it was at 5 characters, but it's not. So it's the minimum length, which is perfect. So we can even make this a little bit longer, right? So hello world is technically what? HELLO and then space and then WORLD. That would be 11 technically. So if I do 10 as the minimum characters, it should give me a smaller list. And then from here, we can just go ahead and pull up hello world. And it only shows up one time. The length is 12. Oh, it's not. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It is 11. What the hell? Why is it saying 12? Okay, whatever. So one time. It shows one time. Excellent. There we go. What is the virtual address of the call function that displays hello world in a message box? So the virtual address of the call function that displays hello world in a message box. So if we click on the message box right here, it should take me to it. So I think it's this piece and it's this message box right here. And we're looking at the address for the call function. Okay, so inside, when we actually go over here, click on the message box, it brings it to the center of the screen here. And then we have the message box, and this is a call function. So this is what we see right here, the standard call for the message box. And then there are the resemblances of what addresses are. So these things right here that you see right here, these are technically addresses, right? So I tried this one, that was not the answer. And then I tried this chunk, and that was not the answer. And then I tried this chunk. And if you remember, Ghidra, if it can't identify something or if it's generic, it'll give it the fun title at the front of it. And so I tried that one, and that was the answer. So it's the 004073D7. That's the answer for the address of the call function that displays hello world in a message box. So we have officially completed that section. So now let's move into identifying C code constructs in assembly. So as the beginning of this video, I did mention that analyzing assembly code can actually be overwhelming if you've never done it before or if you don't have a background in coding, but it is something that is very important. So what we're going to do in this particular section is to examine the various C constructs and their corresponding assembly code, and it'll help you identify and focus on the key parts of malware during analysis. So you don't have to analyze everything, you just need to find these specific sections, right? So you can load the program present in code constructs as shown below. So what do we have? We have the overall hello world that we see right here. And let me just make sure that it is the same thing, but it says you can load the programs present in code constructs folder in Ghidra as shown below. So they have the project hello world, and then they've loaded all of them into Ghidra. There are different approaches to begin analyzing the disassembled code. So we can look at the main function of the symbol tree section. We can click on the text from the program tree section, and then we can look for interesting strings and locate the code from where those are referenced. Different compilers add their own code for various checks while compiling. Therefore, expect garbage assembly code that does not make sense. So for hello world, this is the very first program that we try out in any programming language, and it's basically to echo hello world or to print hello world onto the screen. This was the very first thing that I did when I was learning Python. It was the very first thing that I did when I was learning shell scripting. It's like the very, very basic, the very first program that anybody ever creates, okay? So this is the example in C code, and it will print hello world on the console. So main, right, print hello world, that's it. And there are two hello world programs. One of them was the desktop that has the hello world message. The other one in code construct shows the hello world in the terminal, right? So in the assembly, message is hello world, and you can see the code right here. Write the message to std out, which is typically the reference for the terminal display. And this defines the string hello world in the data section and then uses the write system call to print the strings to std out. In Ghidra, if we actually open up the hello world executable found in code constructs, and you know what, while I'm recording this, I'm actually going to, we'll start a new project, right? And then from there, we will go ahead and import all of the other things because, we're going to close all, I guess. So we'll close everything. We don't need to save any of this stuff. And then I'm going to open up a new project, or I'm going to start a new project. And that way, yeah, I feel like I need to just close this out because I don't know how to start a new. Oh, there it is. So this is where we're at. So once you close that out, it actually does that for us. And so we will do a non-shared project in this particular case, and it's going to be the code constructs. I'll name it as code constructs project. That will be our new project. And from here, we will batch import essentially the contents of that full folder. So if I do batch import, or I should be able to import like the entire thing, I want to say. So if we do inside of our desktop, we should be able to go and click on code constructs and select all of those files. And it's going to say batch import. Yes, excellent, great. So we're going to import all of that. There we go. And it imported 5 files, perfect. And these are all of our files. And we're going to start analyzing hello world.exe. And while this is going to be analyzed, we're going to read the rest of our information. So now it's analyzing, it's running in the bottom right. Oh, that was super fast. Okay, so I guess that was it. That was not, I thought it was going to take much longer, but that was really fast. Okay, so all right. So this is the main function, examining the assembly and decompiled C code in the main function right here. We can see it right here, and this is the decompiled C code as we can see over here. And so if we look at the disassembled code in the listings view, we can see instructions to push hello world to the stack before calling the print function. There's a for loop concept. So a for loop is something that iterates for the most part, right? So for X, do this. That's basically what it is. It's like for A, do B. For condition, do action. That's essentially what it is. They also call it a conditional statement. Or actually, no, I'm sorry. An if statement is the conditional statement. A for loop is an iterative statement. So the following code shows a simple for loop, right? So it says for integer equaling 1. If the integer is less than or equal to 5, add 1 to it and then print it, essentially, is what it does. And in assembly, let's see. Yeah, so this is going to display a message 10 times, which I don't see the 10 part of it because it says less than or equal to 5. So maybe I'm misunderstanding this. So that could very much be the case. But this is the simple for loop displaying the message. The for loop in assembly does the same thing. So loop 5 times as I thought it was supposed to be, but this is what it looks like in assembly. The main function initializes the loop counter ECX to 1 and the loop limit EDX to 5. The loop label is used to mark the beginning of the loop. Inside the loop counter is printed to the console using print from the standard library. After printing the loop counter is incremented and the loop limit is checked to see if the loop should continue. The loop continues if the counter is still less than or equal to the loop limit, which in our particular case, it should be 5. I don't know why it said 10 in this other one. That part doesn't make sense to me because it literally says less than or equal to 5. So maybe that's kind of like an issue, or maybe like a misprint or something. But same thing here. We have loop 5 times, right? So it's technically telling us that it's going to loop 5 times. And then if it exceeds the loop limit, the loop terminates. So if it goes greater than 5, it'll stop running. And the control is passed to the end of the program where the program returns 0. For loops in Ghidra. So if we open the for loop executable program that was found in constructs, we can look at the executable. And so this was, I guess, the main section right here. So it makes a, what is it? Let's see, this program demonstrates for loop statements for local 14, etc. And it will go ahead and check it against the local 14 variable. And let's see what the explanation for us says. It says we can see how the for loop is translated into disassembled code. So I guess, yeah, so this is what it is, and it's translated into disassembled code that tells us that the main function does all of those things. Or maybe this is the disassembled code, because when I look at this, yeah, in assembly, this might be, yeah, this is the for loop displaying a message 10 times. So maybe, yeah, this is the disassembled code. So I want to say this is the disassembled code, I think. I'm still not 100% sure on this stuff, so I apologize if I am misinforming you. I do apologize sincerely. A function is a key component of any program language. It's a self-contained block of code that performs it. So this is one version of it. In assembly, this is what it looks like. And the add function starts by saving the current base pointer value to the stack. Then it sets the base pointer to the current stack pointer value. The function then moves the values A and B into the EAX register, adds them, and stores the result in the result variable. So let's see if we can actually look at all of these things and see if we have it. So this is the disassembled version of it. This is the actual function itself. This is like the block of code in C. So you can see integer A, integer B, the result is A plus B, and it's stored inside of the result variable, and then the result variable, the data that's stored inside of it is returned into our program so that we can use it for future references. So it's very different than this is obviously much simpler than what we can see right here, right? So this is the add function, and it's going to do all of these things inside of 4 lines of code technically. So what else do we have here? The function moves the value of the result into the EAX register, restores the previous base pointer value, and returns to the calling function. A while loop typically says, while this condition is true, I want you to do this. When the condition becomes false, then I want you to stop doing it. So in this case, the integer is 0. If the integer is less than 10, then you're going to print this, and then you're going to add 1 to the integer. And then so it starts at 0, then it's going to be 1, then it's going to be 2, then 3, then 4. And then when it gets to 9, it'll still be true. As soon as it hits 10, it's going to become false, because it's not saying less than or equal to, it's just saying less than 10. So as soon as it hits 10, it will become false. The response here will then be, this is false. This condition is now false, because as long as it's less than 10, the condition is true. So while this condition is true, you're going to do this. As soon as the condition becomes false, you're going to stop doing this. That's basically what a while loop does. And this is what it looks like in assembly. So the move instruction initializes the register ECX to 0. And so we can see it. I think it kind of just gives us everything line by line here, right? So the move instruction initializes the register ECX to 0, representing the variable I. The loop start label marks the beginning of the loop, and we can see it right here. The CMP instruction compares the value of ECX to 10. If ECX exceeds or equals to 10, the loop ends and the program jumps to the loop end label. Otherwise, the value of ECX is pushed onto the stack along with the format string and the value of ECX itself to be printed using printf. The add instruction cleans up the stack after the printf call. Finally, the value of ECX is incremented and the program jumps back to the loop start label to repeat the loop. So all of this says this right here. It's actually very interesting that the disassembled version or the assembly version of the code is so much more complex looking. But I think it's because it's literally saying it's going to compare the integer to 10, and then if it doesn't, or if it exceeds it, it's going to stop it, or if it's still less than 10, it's going to run it again, etc. So it is interesting the way that assembly code actually looks like and the way that it works. It kind of explains this structure for us, right? And if you still don't know exactly how to understand this information, like if you don't know what push means and if you don't know what call means, and push means that it's saving the value of it to the stack, right? It's pushing it to the stack, pushing the format string for the for, pushing the word, the value for I into the print, and then we're going to call printf to print a value. So we're now calling on this function to do something for us. Now we're adding something, we're incrementing something, and then we're going to jump back to the start of the loop unless this is now either 10 or greater than 10. If it's greater than or equal to 10, it's going to jump to loop end, meaning the loop is going to stop. So this is really the full explanation of the actual 4 or 5 lines of code. It's just that you got to know these very basic pieces right here. The syntax right here, if you just understand what push and call and I mean, you can understand what add means. You can, hopefully you can understand what increment means. So at the very least, this piece, it tells you what the step is that it's trying to do in that specific element. So I like that. That's pretty cool. A while loop in Ghidra. So if we're going to open up the while loop program in Ghidra, go to the functions, and in the symbol tree, locate all the main function. And then we can see that right here. So this is the assembly. Now I fully understand that this is actually the assembly. This is the code itself. And then it's just going to run it, right? In this program, a text is printed 5 times until the value of the counter variable reaches 5. We can observe the assembly instructions on how the counter variable is set, how the loop works, and how the program uses the jump instructions to satisfy the conditions. It's important to note that different compilers would compile the programs differently, adding compiler-related code. To demonstrate, the programs used in this room, in this video, are compiled using different compilers. Therefore, you may find difference in the interpretation of assembly code. We're going to examine the if-else executable and the while loop executable and answer the questions below. So what value gets printed by the while loop in the while loop executable program? So I actually opened up Hello World, so I'm just going to close this thing out. I don't want to save it. I will open up the while loop executable, and hopefully this one also will load as quickly as the other one did. It'll be analyzed as quickly as the other one. So let's see how long that one takes. And then the question specifically is asking what value gets printed by the while loop in the program. So we want to see what the value that is going to be printed for us is going to be. So we're going to go through, let's say we're going to go through data, and then let's see if we can file that, or maybe inside of the functions maybe. Let me see what I can find here. Okay, the main function, this was the hardest part for this, was to try to find the actual location of the main function because things are abbreviated here. So if we actually go inside of the functions and then expand the first one right here, which is represented by the underscore, once we expand that, we have a bunch of other things inside of it. And then if we go down here, there is one that is underscore m, and then inside of underscore m, there's the main function. And then when you click on that, it is automatically highlighted, and then on the right side, we actually see the code itself. And then so it says this program demonstrates the while loop for etc. etc. It's going to print it's fun to learn at THM. And so we're just going to highlight that portion, and let me see if I can copy that. Okay, great. And we're going to go over here and we're going to print it, and I believe that's going to be the answer here. Very good. All right, so how many times the while loop will run until the condition is met? Okay, so let's see. How many times will the while loop run until the condition is met? So technically, I think it's going to be 4 times because it says less than 5. So if local 14 is equals to local 14 plus 1. So local 14 starts at 1, so that will be the first iteration. Then it'll go to 2, then it'll go to 3, then it'll go to 4, and then it'll stop at 5. So it should run 4 times. That would probably be the answer. Let's see. Yeah, that is the answer. Excellent. Examine the while loop executable in Ghidra. What is the virtual address of the instruction that calls to print the sentence? That's the end of the while loop. So this is it right here. And so we're looking for this piece right there. And what I'm looking for here is the virtual address of this. So what we're going to find right here, this is it. This is the one that says that's the end of the while loop. And the virtual address, I believe, is this piece right here. So let's see if that's actually the right answer. Hopefully it is. Okay, so that was not the answer. And so if we actually right click on this, or not right click, if we actually kind of hover over it, it says on the screen, I can't move the mouse because it'll take it away, but if you look at the bottom right here, it says address, and then it says 00404040. So I'm going to say that that's the address. So we'll do 00404040. And that is also not correct. That is so funny. Why is that not the address? It literally says address. Okay, so here is the answer. And so that makes sense. The way that we find the answer is we're looking for this thing right here. So technically this variable right here is what is being called to print. That's the end of the while loop. So we're looking for underscore puts. And then if we go to find the call to underscore puts, which is this piece right here, this ends up being the address of it. So it's this point, this piece right here. That actually is the address that we're looking for to pull that off. And there you go. That's the answer. So understanding the syntax, understanding what we're actually looking for is more like 80% of the battle in this particular case. And I did not understand what I was looking for. I was just looking for this phrase, and then when you try to find the phrase, it's right here, and then it literally says it. It's kind of hard to see right here, but it says that's the end of the. So I'm looking at this whole thing. I'm like, oh, that has to be the answer. So I tried that. It didn't work. I tried this address right here. That didn't work. I tried this address. That didn't work. And I was like, okay, well, what the hell am I missing? And then now you can see that there's a call to the puts variable, which is what we actually see right here. So that was the answer for that. Now, in the if-else program, examine the strings and complete the sentence. This program demonstrates, etc. So we're done with the while loop. We're going to move on, and we're going to open up the if-else program here. And let's analyze it, and let's see how long this one will take. Okay, that was actually super quick. It was like literally like 2 seconds, not even. Okay, so we're going to search for strings in this whole thing, and the string itself right here is that this program demonstrates. So here's what I'm going to do just to make my life a little bit easier. I'm going to do a character counter, and then I just want to see how many characters that is. So that is technically 25 characters. So I can at the very least say that the minimum that I'm looking for is 25 characters, and I only want strings of that length. So it should be, and it's literally at the very, very top. This program demonstrates if-else statement. So I guess we'll just put the full thing. This program demonstrates if-else statement. There we go. Excellent. So what is the virtual address of the call to the main function in the if-else executable program? So there we go. So now we know what that means, right? So we first need to go ahead and find the function for the main function. And based on what I saw previously, I wonder if it's the same thing. So under underscore, we're going to go down here. We're going to go to M for the main, and we're actually going to click on the main. And here we go. So this is the main function. And on the right-hand side, we actually also see the integer, etc., etc. So if I click on this, or maybe click on that right there, it should take me to it. And now we can see call on the main function, and we have this number right here. So I really think that this is the answer, and I hope that that is indeed the answer, because I would love to get it right on the first try, and it is the answer. Great. So I learned something today. Or I mean, I'm learning a lot today, but that was cool. Okay, so now we understand what it means when we're calling on something and we're looking at assembly code and what that actually means and how to find those addresses. Super excited. I feel like I'm growing. This is great. All right, let's go to the overview of Windows API calls. The Windows API, if you've never heard of it before, the API stands for the the Application Programming Interface. This applies to very many things, and the concept of an API call is something that you will hear about a lot, and the integration between different applications, right? So when you connect one application to another, for example, Coinbase can pull money from a bunch of different banks so you can fund your Coinbase wallet, your Coinbase account. And to be able to do that, the Coinbase application integrates or connects with the APIs of all of the other banks. So that is one of the biggest uses that is available for API. Now, what happens is that you make a call on the functions within that API. So for example, the Windows API has a bunch of functions that you can call upon, and then each one of those functions does something different, right? So in this particular case, it's the collection of functions that services the Windows operating system, and it provides it provides to enable the developers. This is a very interesting syntax, like the way that this room has been written out. It's a very interesting syntax. And I'm an immigrant, and I have no problem with people who are immigrants that write things out. But this very much feels like it was written by somebody who English is not their first language. And I love that, and I think it's amazing. It's very inspiring because it goes to show that English does not need to be your main language for you to create a freaking room in TryHackMe. You know what I mean? It's pretty amazing. Let's see if we can see who the user is that created this room, because Dex01, this guy right here. So let's see what we can get for Dex01. This guy, I'm sure, oh, it's on the staff, passionate about teaching and learning new things. We love Dex. There we go. Pakistan. See, there we go. My guy. So his streak is at 0 because I guess he hasn't done a lot of things in TryHackMe. I have a higher streak than him, which is 2 right now. David, one of our members inside of Hackaholics Anonymous, has a streak of like 500 or some crazy thing like that. So I'm digressing, obviously. I've also completed more rooms than Dex, so I can confidently say that I feel like I'm a little bit better. Not at all, because Dex literally created the room that we are in, and Dex is teaching us all these things. So just because he hasn't completed many rooms does not mean that Dex does not know what he's talking about. Clearly, he knows what he's talking about. So shout out to Dex. I should probably start doing that, like giving a shout out to the people who created these rooms. I think that would be like a cool little new addition to these things. So I'm going to start doing that. If you're listening to this right now, you're witnessing history. I've decided that I'm going to start giving a shout out to the people who created these rooms for us. So these functions inside of the Windows API includes creating windows, creating menus, creating buttons, and other user interface elements, and performing tasks like file input output and network communication. So we have an example right here, the create process API, which is a really common one that is used all the time by Windows machines, whether or not you know it, right? When you open something, when you open an application, it creates a process. So it creates a new process and its primary thread, right? The function takes several parameters, including the name of the executable, command line arguments, and security attributes. The syntax in C++ looks like this, okay? Just to keep that in mind, you don't necessarily need to know what this is, but this is the create process API call. So this is the C code that uses the create process function to launch a new process. We have this right here, so you can see right here. Again, I'm not going to go read through this line by line. When compiled, the create process looks like this. So not that complex compared to everything else that we've seen, compared to the loops that we saw where there was like 5 lines of code and it was like a really long assembly description. In this particular case, not that much. So the assembly code pushes the necessary parameters onto the stack in reverse order and then calls the API, the create process function. The create process function then launches a new process and returns a handle to the process and its primary thread. During malware analysis, identifying the API call and examining the code can help understand the malware's purpose. So, when a process is created in suspended state, which hexadecimal value is assigned to DW creation flags parameter? This is interesting. So now I actually have to find some information about that because I don't even know what that is. I have to actually find the answer for that. I don't think it's inside of any of these things right here. So looking at it in a suspended state is what they're telling us. And we were trying to see, okay, so what is the question? And it says, right, read the Microsoft documentation, obviously. So instead of doing that, I'm just going to Google this thing right here because it's basically the same thing as reading through the documentation. So process creation flags, here we go. And we're looking for the suspended state, created in a suspended state. I think it was actually in the basic description right there. So the process, so let me find the answer real quick. Okay, so on the Microsoft documentation, I literally did a Control F or Command F, and I went and found create suspended, and this is it. These are the only 2 references of the word suspended, and then this is what we have for the hexadecimal value. So that is the answer for us over here. Now we're going to explore Introduction to Windows API Room to learn more about Windows API calls, and I want to say I've done this. I'm not sure if I have, but I feel like I have not done it. Okay, great. So this is what we're going to do. We're going to go ahead and pull up the Microsoft documentation page one more time. And we're going to leave this open because I feel like, or maybe not even that, like we should be actually pulling up Windows API calls. So let me just pull up the Windows API calls. And then from there, we'll just have that available for us. Programming reference for Windows 32. And then, yeah, Win32. So hopefully this will actually be useful for us as we go through the rest of the content here. Now that we understand what these common APIs or what the APIs in general are, we need to look at the common APIs that are used by malware specifically. And it's an important step in advanced analysis, in advanced static analysis, to examine all of the import functions, which can reveal everything about the malware or a lot about the malware. And it's basically everything that is going to be inside of the import portions right here that we see right here, right? So if I expand on this, we can see that there's the kernel 32 DLL, and then we have the MSV CRT DLL, and inside of them, there's a bunch of different functions that are being pulled in. And same thing for the kernel, and then we can see delete critical section, get current process. These things are they seem like the commandlets, right? So if I go ahead and, for example, open up PowerShell inside of this Windows machine here, and we can literally just do get processes or get process, I think. So let's open up Windows PowerShell just so you can see that these things actually translate into a command, right? So if I do get process, there you go. It just lists all the processes inside of this specific virtual machine that is currently running right now. So that's a commandlet, right? So get process is a commandlet. And in this particular case, it just says get current process. So it's not hyphenated. And usually commandlets inside of PowerShell are typically hyphenated, as you can see right here. If I do get current process, I don't know if that'll actually work for me. It doesn't. So what it gives me right here is that there is no object that has been found. In this particular case, it's not recognized as the name of a commandlet. Script or file, check the spelling of the name. If I do get hyphenated and I do get current process, that also does not work. So maybe that is not an official commandlet, but I do know that get processes is one. And essentially anything that I see like this, I just immediately associate this with some kind of a commandlet. So if there's a get current process API call, we can try to see what the commandlet equivalent of that is, right? So what is the commandlet for the get current process API? Let's see if that gives us anything. And it just says get process. So I guess that is it. That is the one that I found specifically, and I guess I knew one. I knew one off the top of my head, right? So you can do the same thing that I just did if you want to find out what the actual commandlet is for any individual API calls, and you'll advance your knowledge that way. So this is one of the ways that I learn things, is that like as things happen and as I'm exposed to information, I'm like, okay, well, let me see what this means and let me see what that means. And then I just kind of do research individually for each one of these different elements, and I learn as I go. So there are a few different ways that you can learn. That's my preferred method of learning. I just learn as I go. Okay, so moving on, the key logger. There are several API calls for key logging. We can use the set Windows hook X, which installs an application-defined hook procedure into a hook chain. And malware can use this to monitor and intercept system events like keystrokes or mouse clicks. So set Windows hook X is one of them. Get async key state, and it retrieves the status of a virtual key when a function is called. It can use this function to determine if a key is being pressed or released. Get keyboard state retrieves the status of all virtual keys, and this can be used to determine the status of all keys on the keyboard. And get key name text retrieves the name of a key, and malware can use this to determine the name of the pressed key. So these are various API calls that can be used to create a key logger, right? So malware can intercept and record keystrokes using any of these things, and it allows the malware to capture sensitive information like passwords and credit card numbers and credentials and just the activity of somebody doing something inside of the given computer. Then we have the downloader. The downloader malware is a type of malware designed to download other malware onto a victim system, and it can be disguised as legitimate software or files that are spread through malicious email attachments, software downloads, or exploiting vulnerabilities in software. Downloaders can use various Windows APIs to perform their malicious actions. Some of them are these. So URL download to file. It downloads a file from the internet and saves it to a local file. And it can be used to download additional malicious code or update to the current malware. WinHTTP open initializes the WinHTTP API, which can be used to establish an HTTP connection to a remote server and download additional malicious code. WinHTTP connect establishes a connection to the WinHTTP, it connects to a remote server using the WinHTTP API. And it can be used to connect to a remote server and download additional malicious code. And then WinHTTP open request, which can essentially do all of the same things. There is the invoke web request, which is, invoke web request, which is a lot of times abbreviated to IWR as well. That's another thing that I've seen in previous exercises that makes a web request an internet request, so to speak, and then that can be used to download data. Then we have the C2 communication, so something known as the command and control server, which is a remote server. And a C2 communication is a method that's used to communicate with the remote server or the attacker or a proxy server, essentially anything that is not in the local network. And now there's a connection that's been established from the local computer to this remote server, and data is going back and forth. Commands are going back and forth via this connection. This can be used to receive commands from the attacker, send stolen data to the attacker, or download additional malware onto the victim system. Internet open is something that initiates a session for connecting to the internet, and it can be used to connect to a remote server and communicate with a C2 server. Internet open URL opens a URL for download, and it can be used to download additional malicious code or steal data from a C2 server. HTTP open request can be used to send HTTP requests to a C2 server and receive commands or additional malicious code. And then, of course, send request that can be used to send data or receive commands from a C2 server. Data exfiltration. So as the name implies, you're just exfiltrating data. You're extracting data, moving data out of the current network into a different location. It could be somebody else's C2 server. It could be a cloud storage location. It just depends how they want to exfiltrate their data. Internet read file reads data from a handle to an open internet resource. And malware can use this to steal data from a compromised system and transmit to a C2 server. FTP for the file transfer protocol. FTP put file is something that uploads a file to an FTP server, and it can use this function to exfiltrate stolen data. Create file creates or opens a file or a device, and it can be used to read or modify files containing sensitive information or system configuration data. Write file writes data to a file or a device. It can be used to write stolen data or to a file and then exfiltrate it to a remote server. And then get clipboard data, which is to pull data from the clipboard. So when you copy and paste something, usually when you copy something, it's copied to your clipboard. And then when you paste it, it pastes from the clipboard. And this can be used to retrieve sensitive data that's copied to the clipboard. A dropper is a malware that's designed to install other malware into a victim system. So it drops other malware, right? It can be disguised as legitimate software or files, and it can spread through the malicious email attachments, software downloads, or exploiting vulnerabilities. Create process is a function that creates a new process. The thing with this is that it can generate so many false positives because all of the legitimate processes on the computer also have a create process commandlet that's running in the background, and it was called at some point to open up all of those legitimate processes. So it is something to keep an eye out for, but this specific search, if you're looking for this, you will most likely find a lot of noise and a lot of data because all of the legitimate processes and applications that have been running also called on the create process API. Malware can also use this function to execute the code in the context of a legitimate process, making it more difficult to detect and analyze, which is why it's so attractive to hackers. Virtual allocation reserves or commits a region of memory, also known as the random access memory, within the virtual address space of the calling process. It can be used to allocate memory to store the code of the malware. Write process memory writes data to an area of memory within the address space of a specified process, and it can be used to write its code to the allocated memory. API hooking is a method that the malware uses to intercept calls to Windows APIs and modify the behavior. So think of it as a man-in-the-middle type of an attack. It allows the malware to avoid detection by security software and perform malicious actions such as stealing data or modifying system settings. And it can be done through getProcessAddress, which retrieves the address of an exported function or variable from a specific or specified DLL dynamic link library. And it can be used to locate and hook API calls made by other processes. Load library loads a DLL into a process's address space. Malware can use this to load and execute additional code from a DLL. Set Windows hook X is the, I think that stands for executable, I want to say. And it's used to install a hook procedure that monitors messages sent to a window or system event, and it can be used to intercept calls to other Windows APIs and modify their behavior. Anti-debugging and VM detection. These are some of the key things that we saw in previous rooms and videos as we were investigating these various malwares. Anti-debugging, anti-VM was the one that I saw specifically. And so these are techniques used by malware to evade detection and analysis by security researchers. So we have is debugger present, right? It's checking whether a process is running under a debugger. Malware can use this to determine whether it's being analyzed and take appropriate action to evade detection. Check remote debugger present. Checks whether a remote debugger is debugging a process. Malware can use this function to determine whether it is being analyzed and take appropriate action. NT-query information process retrieves information about a specified process, and it can be used whether or not it's being debugged and take appropriate action. Get tick count retrieves the number of milliseconds that have elapsed since the system was started, and it can be used to determine whether it's running in a virtualized environment, which may indicate that it is being analyzed. Get module handle retrieves a handle to a specified module, and it can be used to determine whether it's running under a virtualized environment. Get system metrics retrieves information, system metrics, right? Data and configuration settings, and it can be used to determine whether it's running in a virtualized environment. So details on this are discussed in the anti-reverse engineering room, which is something that I know I have not done. And there's so much stuff inside of TryHackMe that it's just really, really powerful information. And I haven't even scratched the surface, I feel like. There are so many more things that I can do. And they're constantly coming out with more rooms. So that's just really, really cool. So we have a resource here where it says read more on malapi.io to learn about APIs used in different malware families. So this is a malicious API database. Look at that. Wow. This is amazing. This is one of those things that is very, very useful to have access to. Man, I feel like I should be storing all of these things. And you know what? I am going to store this one. This is actually a really useful one. malapi.io. That's very useful. I'm going to keep that one. All right, great. Moving on to the next piece. Now we can add on to the information that we've collected so far to learn about a concept known as process hollowing, which is a part of detection evasion, and it's a process injection technique. So process hollowing is a technique that malware uses to inject malicious code into a legitimate process that's running on the victim computer. The malware creates a suspended process and replaces its memory space with its own code. Then it resumes the process, causing it to execute the injected code. So we actually looked at something, not in this one. I think it was in the previous, in this particular place, where I think we were looking at suspended, right? That was like one of the things that I was looking at for the API calls. Yeah, it is. So creating suspended processes this is one of those things that is referencing right here. So process hollowing will use the create suspended API call, right? So the technique allows the malware to bypass security measures that may be in place as the malicious code is executed within the context of a legitimate process. Process hollowing is achieved through these steps. So we have creating a new process using create process. This process will act as a legitimate process and it will be hollowed out. So think about the shell of a process being created and then it's suspended, right? So a legitimate process is created. The process is then suspended and then it's hollowed out. And then it will be rewritten, like the content of that process will be rewritten so that it can do what the attacker wants. So first the process is created and it looks legit. Then the process is suspended and then there's allocated memory to it. So we do virtual allocation. This will be used to hold the malicious code. Then we write the malicious code to the allocated memory using write process. Then we modify the entry point to the set thread index and get thread index APIs. So to the point to the address of the malicious code, right? So we have allocated memory, virtual memory that's been reserved so we can write the code to it. And then inside of that virtual memory, we do whatever we need to. And then we modify the entry point of the legitimate process, right? So we modify the entry point of the legitimate process to the address of the malicious code inside of that virtual memory. And then we resume the process, the suspended legitimate process. We resume it and it will cause the process to execute all the malicious code. So it's kind of cool when you really think about it. So you have the malware process, right? So this is the actual target process, the legitimate process. We hollow it out, we transfer the malware code into it, and then we resume it, and then it'll just work. It'll work as if it was its normal thing, but it's obviously running the malicious code. So this is a sample C++ code that kind of demonstrates this. So we're going to use namespace std, and then we have the hollow process function that's been created, and essentially it's going to create tools help 32. What is it? This is one API call that's being made, and it's going to take a snapshot as it needs it, and then we are going to start running the individual processes, right? So it's going to open a process, it seems, and then it's going to let's see, read the process memory. It's going to allocate virtual space to it, and then it's going to write to the process memory, then read the process memory again, write to the process memory again. And if this is not available, so if when we put exclamation, typically exclamation means not. So if this is not available, or if it's not functioning, or if it's not useful, I'm kind of trying to call on from my Python knowledge. So if it's not available, it's going to return false, and it's going to close the handle and break the entire cycle. It's going to break the overall loop that is going on. Apart from that, it will actually go ahead and work, and it's going to, if this is not available either, so if the create process is not available, and if it can't do it, it's going to return as false. If the get thread context is not available, it's going to return as false. If set thread context is not available, it's going to return as false, and everything is going to be closed. Apart from that, if all of those things are not there, so if it's not available, meaning if it is available, then it's going to return as true, and then it's going to go into the main function where it will actually act as the hollow process. The process itself will actually start running, and it's going to tell us that yes, it was successful, and if it wasn't successful, it'll say process hollowing failed. So this main function is going to call on everything else that was created up until this point. Everything else that we've done up until this point is going to be called in that main function. And so we have the hollow process itself. That is the main function. That is all of within this is everything else that you see right here. And there's a bunch of if statements. There's a bunch of, if this is cool, do this, right? If this is cool, do that. If any of these things are not okay, just return false and then ultimately break. But if it is okay, then I want you to go ahead and run the snapshot, do everything that you're supposed to do. And then if that create process can't be run, just return false, etc. So we've already kind of reviewed this. This is actually a pretty lengthy script right here. And for the most part, I'm kind of deducing based on what I know from Python, but it is fairly, it is resembling Python in a sense. Usually you don't use these squiggly brackets in Python. You usually use parentheses in Python. Squiggly brackets are mainly used to house data, to house dictionaries of data. So in this particular case, all of the function commands are inside of the squiggly brackets, but for the most part, it is relatively similar to what goes on inside of Python, and then we can just kind of deduce what we know that way. But for the most part, we also know that this is going to do exactly what process hollowing is, which is something that we've already discussed. So we can kind of understand that this entire script is just trying to check for the availability of virtual memory, the availability of certain processes, and if those things are available, it's going to go ahead and hollow them out and then replace them with what the original code is, or what the malicious code is that is supposed to be. So now we're going to analyze the benign.exe in the lab, and we're going to see which API is used to write malicious code to the allocated memory during process hollowing. So let me go ahead in our virtual machine here. I can close malicious API. I'll close that as well. And then we'll go into here, and then we're going to open up benign.exe, which is it even in here? Oh, it's not. So I can actually drag and drop it. Let me see if I can drag and drop it into here, and we can just kind of use it as one of our executables. And so we do have that. So we'll just open that up and we will analyze it, and let's see how long this takes. That was actually very quick as well. So, all right, so this one loaded in a few seconds. So we are looking for the import function, right? So we're looking for all of the stuff that is used to allocate memory during process hollowing in this particular specific benign one. And so we know that there are several functions that can be used to allocate memory, right? So virtual alloc ex is one of them. And then when we look at the common APIs that are used by malware, we can actually look at those as well, because there was an entire section for allocation, the virtual memory allocation, or I thought there was, but I guess it's not, or get process address, maybe not. Okay, so I will just go ahead and see what I can find inside of all of the imports that might be relevant to virtual memory allocation. So we're going to go over here, we're going to click on imports, and let's see what we can find here. So in the kernel DLL, so inside of the kernel 32 DLL, towards the bottom, we can see that it has the virtual allocation EX, virtual free, write process memory. So if it's looking for, it says to the allocated, which API is used to write malicious code to the allocation. So I would say write process memory. That might be the one. So write process memory. I think that's it. And that is the answer. Yeah. So there is the specific parentheses that I was supposed to add to the end of it, which I guess I didn't add because I didn't know that I was supposed to add parentheses actually. But the answer is correct. They just added the parentheses for me. So it is write process memory that's used to write malicious code to the memory during the process hollowing. Very good. So now let's go and look at analyzing process hollowing, and then we'll wrap this thing up. All right, now we're going to do a full-on analysis of the benign executable that was on our desktop. I already have it open, so thankfully we will be able to kind of run and gun immediately. An important point to note is that almost all malware comes packed with known or custom packers, and also have employed different anti-debugging or anti-VM detection techniques to hinder the analysis. This will be covered in the next video that we're going to do. This specific sample is not packed, and so now no anti-debugging or VM detection technique is applied either. And the objective is to examine the API calls to find a pattern or suspicious call, look at the suspicious strings, find interesting or malicious functions, and examine the disassembled, decompiled code to find as much info as we can. So once we load the sample, we can go ahead and essentially go after the various functions. Now, Ghidra does not automatically land at the start of the program, and it's up to us to find out where we want to start analyzing. And it's also important to mention that starting to search for create process A is not how an analyst would start analyzing an unknown binary. So that being said, they're going to have us do the very first thing, being create process A. But they did note that, I guess, in a real world, that's not the first thing that you would look at. So I'm kind of confused, but it is what it is. Okay, so we learned in the previous task that the suspicious process creates a victim process in suspended state. So to confirm, we can search for create process A in the tree section, then right click on the show references to display all the program sections where the function is called. So we will go, I'm just gonna literally do this. So I'm gonna go over here because I feel like it might be better to kind of go along with this whole thing. So there's create process A right here. I'm gonna right click on it, and then I'm going to show references to this, and then it's gonna show me 2 references right here. Perfect. Okay, great. So we just do this, and then it gives us the same 2 references. Clicking on the first reference will take us to the disassembled code and show the decompiled C code in the decompiled section, as we can see right here. It clearly shows how the parameters on the stack are being pushed in reverse order before calling the function. The value 0x4 is being pushed into the stack. So we can actually see right here, it's right here. 0x4 is the value that's being pushed. And based on the IDs that we gathered, right, that's the create suspended API call that's actually being called upon. That's the create suspended function. Clicking on the display function graph in the toolbar will show the graph view of the disassembled code that we're examining. And then we can see that right here, 0x4 is right here. And it'll take us to this portion right here where it gives us the call, push, etc., all of the various elements of that. And then finally, we will have this section here. So in this case, if the program fails to create a victim process in the suspended state, it will move to block 1. The red arrow represents the failure to meet the condition. So if it fails, it'll move to this, right? If it fails, it'll move to this. If not, it'll move to block 2. It successfully creates the victim process, it'll move to that, and that's what the green arrow represents. So we then open the suspicious file. So the create file A API is used to create and open an existing file. And we can search for this in the symbol tree section and go to the code, what it's referencing to. Hollowing the process. The malware uses this thing, so ZW unmap view of section or NT unmap view of section to unmap the target process's memory. So we can search for those to see if either API is called. In this case, it's NT unmap view of section. And it takes two arguments, the base address, which is the virtual address, and the handle to the process that needs to be hollowed. Then it allocates memory using virtual allocation X. We can find instances of that, and they're passed to the function, including a handle to the process, address to be allocated, size, allocation type, and memory location. And then right down to the memory. So this will actually use the write process memory API to write to the actual memory and write whatever the code is. And so we can do the references again. That would be reference to this. And we can see that the one that's highlighted is the call dword ptr kernel there were 3 calls to write process memory. The last call references the code in the kernel 32 DLL. Therefore, we can ignore that. From the decompiled code, it seems that the program is copying different sections of the suspicious process one by one. Then we do resume thread. So once it's all sorted out, the malware will get a hold of the thread using the set thread context and then resume the thread using resume thread to execute the code that now has been written on top of the hollowed portion. So we can see right here, set thread context, and then we can see resume thread right here. Now we can see the program sets the thread and then resumes it. So what is the MD5 hash of the benign exe sample? So, I mean, one of the easiest ways that I know to do this is to actually just use PowerShell to do this for me. So let me see. I think it's get algorithm. Let me find out exactly what it was. I just need to remind myself. So this is it. So we're looking for the desktop. That's where benign is located. Excellent. So this is the command itself. So once you're actually in the location that you need to be, it is get file hash, and then the file, or the path, excuse me, is going to be this one right here, which is going to be benign.exe. That's the file itself. And then the algorithm is going to be MD5, I want to say, like that. And so there it is. So there's our get file hash of the benign executable. So we got that. So I will just copy that real quick, and then we'll go here and paste that here. Great. So how many API calls are returned if we search for the term create in the symbol section? So in the symbol tree, I actually don't know how to search in here. So I wonder if I just do search right here, and we can go for matching instructions maybe, or let me see what I can find. Okay, I feel very silly because it's literally right at the bottom. Usually it's some things at the top where we can do the search, but the filter is at the bottom of this box right here. So if we just put create at the bottom right there, we can search for it, and there are two API calls that are returned to us. What is the first virtual address where the create process A function is called? So we're going to click on this, and the first virtual address where this is called, I would assume that this is the first one that I have right here. So the first call to this address would most likely, I want to say, is going to be these addresses right here. So let me go ahead and see if I can do that. So this is the call right here. And if I highlight that, all I did was when I clicked on this, I can actually click on this, I guess, and it'll take me to the call of create process A, the very first call to create process A. So that's great. And this is the address that's assigned to it that we can find right here. So we will copy this and cross our fingers to make, hopefully that's the address, and it is. Great. Which process is being created in suspended state by using the create process A API call? So what is being created in suspended state? So if we're looking at this, I wonder if it is in this portion right here. So let's see if I can expand this a little bit and see what I can find. And it's actually right here. So if we just zoom in on this a little bit, we can see that create process A, it has this program files path, etc., and it has I explore executable. So we can just highlight this piece right here and then copy that and bring that back over here. And that would be the process. So what is the first virtual address where create file A is called? The first virtual address where create file A is called. So this would be the bvar2 right here. So that's the piece that I would be interested in, I want to say. So the call of bvar2, I think, is what we're looking for. I stand corrected. I apologize. This is create process A. We're now looking for create file A, which is this guy right here. So if we look at create file A, we can see the first instance showing up right here. And then this is the address that I have here. So if I call that, we can see, or if I double click that over there, it'll bring us to the first call, which is this address right here. And let me see if I can highlight this guy. Okay, there we go. And so we have this. So we're going to copy that and we're going to go over there, and that would be the address. What is the suspicious process being injected into the victim process? So create file A. Let's see if we can find how this is being referenced here. This is what we got. And evil.exe. That's the injector. So THM attacker desktop injectors evil.exe. Very obvious name. It's not going to be that obvious in the real world. Let's just address that right now. Based on the function graph, what is the virtual address of the code block that will be executed if the program doesn't find the suspicious process? So I guess we're just going to do this right here, and we will go and create, what is it, the function graph, I think, display memory map, function graph, there it is, that's the button. So the button, let me close this real quick just so I can show you this one. This is the create function graph. So if I click on this, there it is, and let me see if it'll bring anything for me. Location is not defined or undefined function. Okay, so that's not it. So let's see if I do right click on this, go to show references and try to find this one maybe. So that one, see if we can find that. Okay, wow, that's a lot. And let's zoom in here. And so it's saying what is the, so what's the thing? It says what happens if the program doesn't find the suspicious process. So we're looking for the address of the code block that will be executed if it doesn't find it, which I think is this. So if it doesn't find a suspicious process, it's looking for this. So I'm gonna venture a guess that this is the portion right here that first is trying to find the suspicious process, because I can't be. Let me read through this a little bit. Okay, once we get past this very first block, so this is the very first block. There's no actual name assigned to it. It just has fun, etc. And then it goes right here. If that one doesn't work, it'll push here. If it does work, it'll move on to this. And if it moves on to this, this is what we have. Can I zoom in a little bit more? I can't. So this is what we have here. So it says created victim process is what it's trying to push in this case. And so if this one fails, it moves to this. And this is what I'm assuming is the one where it's actually trying to find that malicious process, or it's trying to create or find that malicious process. And so if this fails, then it'll move to this piece right here, which will be 401.101. So 00401.101. And that is the correct answer in this case. Which API call is found in the import functions that's used to unmap the process's memory? So we have one of two options that were available to us. It was either the, where is it? Not the NT unmap, or it is the ZW unmap. And we're looking for either of those. So now that I know that I can actually search through the symbol tree here, I'm just going to search for unmap. And in our particular case, it is NT unmap view of section. That is the one that's been pulled. So I'll just actually copy that and go down here and paste that here. How many calls to the write process memory function are found in the code? And we're going to be looking inside of the text section. So we're going to go inside of this, inside of the text section. Let me see if I can pull that up. Okay, very good. And so we want the calls to write process memory function. Okay, so I tried a few different approaches to try to find this. First of all, I clicked on the text, and then I upload, like literally double click text, and it brings me to the overall thing. And then trying to search through this was a little bit difficult. I went through search and I searched for strings, and inside of the whole thing, I looked for write process memory. And for write process memory, only one string actually showed up. So this was not helpful, I don't think either. And then I obviously went to the symbol tree here, and then I looked for write process memory, and then I clicked on that, and then it brought it up for me here. And then we have the address here, and I double clicked that, and it took me directly to the call that I have here. But then I wasn't able to try to find other instances of it, because it just, every time it just brings me to this specific address. But what happens is that when you double click this and you go over here to the call for the process memory, we have the call to this address right here. There's this X reference to, and I want to say that means that it's referenced twice, if I'm correct. So is 2 the right answer? 2 is the right answer. I am not 100% sure that that's actually what this means right here. So I'm gonna go try to see if I can find out if what this actually means right here. So let me go see if I can find some more explanations for this for us. Okay, so I think it is the correct deduction that we have here. So typically XREF stands for cross-reference, and in disassemblers and analysis tools, cross-reference indicates a location in the code where a particular symbol, like a function or variable, is being referenced or used. To, in this particular case, usually signifies the number of distinct locations in the analyzed code for the cross-reference. So therefore, this strongly suggests that the function is called for twice within the analyzed malware. So There we go. We got that as a little bit of a confirmation for us. Now it says, what is the full path of the suspicious process shown in the strings? So now we need to just go ahead and find the full path of that suspicious process. To try and find that one, because I do remember that there was a path for the evil executable, right? So if we go ahead and reference that piece right there, so let me see if I can go ahead and find that one more time inside of our code. And then this is what we got right here. So create file, right? Inside of the create file, this is the path that we have. Now the double backslashes may not necessarily be necessary, because one of the backslashes is an escape character. So it's not always double backslash. Oh, actually, no, they do want double backslashes. I think that's it. I think that's the path. There you go. So that is the actual path of the evil executable. That it was the suspicious process that was shown in our strings. And that's the last question. That was nice. I like that. So that was a bit of a learning curve for me. Anyways, I don't know about you. You're probably where you might be even way better at this stuff than I am. But, you know, we made it to the end, thankfully. And we learned the basics of performing advanced static analysis, common APIs that are used by malware, how process hollowing works. And I think the big piece, the two big takeaways that I have from this was, number one, the APIs, the common APIs that are actually used for malicious malware. And I actually stored that bookmark as well, that malapi.io. That was very, very useful. That's actually very useful database for the common APIs that are used by malware. And we can always just reference that and then try to find their associated IDs to try to look for them inside of malware. So for example, the 0x4, where there's a creating of the suspended process, and then how that actually relates to process hollowing and what that actually means, where you create a normal process, you suspend the process, you assign virtual memory for your malicious code, and then you take the address of the virtual memory and you assign it to the entry point of that normal process. And then when you restart the process, or when you resume the process, it'll now execute the malware, the malicious code. That's very, very useful. That's very, very handy information. So process hollowing was like a really big concept for me, where I was like, wow, that's actually really kind of crazy. And as well as all of the common malicious APIs, or common APIs that are used for malicious purposes. Those two were big takeaways for me from this specific exercise. And I hope that you actually got some value out of it as well. And if you were running along with the exercises that we had here, I hope you actually were able to come to those conclusions and find those answers yourself. So all in all, I hope you got value out of this room and out of this video. If you did indeed get value out of this video, and if you've gotten value out of this channel, I do encourage you to like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out on this channel. We are almost done with SOC Level 2. Malware analysis, I think, is actually the last main section in SOC Level 2. So I'm very, very excited about it. I think it's something that has been a long time coming, because I've been trying to get this done. Yeah, malware analysis is the very last one. And we just did advanced static analysis. Then we have basic dynamic analysis, there's dynamic analysis debugging, and then anti-reverse engineering and the maldoc static analysis, which is I think it's like the final exercise that's assigned to us for our specific SOC Level 2 pathway inside of TryHackMe. So I'm really, really excited about wrapping this thing up, and then there's going to be obviously a bunch of content that is going to come out, or at least those last segments that are going to come out for SOC Level 2, and then every Friday, we have PenTest Plus, CompTIA PenTest Plus PT0003, which is the most recent version of the PenTest Plus examination certification that is released from CompTIA, and we're going through that, and that's a really, really cool pathway. So every Friday, a new video comes out from that, And then, of course, we're going to go into CYSA, CompTIA Cybersecurity Analyst. And then we're going to have, of course, the AI for cybersecurity and how to train AI to go into security for you and do all those things. So there's so many things that are going to be coming out on this channel. And I think you want to be around for that. So just make sure that you like, subscribe, and turn on the notification bell so that you get notified the next time that a video comes out. And of course, drop a comment if you have any questions and if you just want to say hi. If you're serious about your CySec education and want access to me on Discord, consider joining Hackaholics Anonymous. We have 4 tiers: the supporter, agent, guardian, and master. Each tier gets their own Discord server and early access to content. The agent, guardian, and master levels get exclusive content, exclusive downloads, monthly Python automations, live streams with me every month, plus so much more. And to join, you can simply click the link in the description below, or you can go to our homepage and click the join button there, or you can go to youtube.com/@HankHacksHackers/join, and you will be able to join Hackaholics Anonymous. I hope I see you in the Discord chats. If not, I hope I see you in the comment section, and that is it for today. So boy, Hank Hackers and at Hank Hacks Hackers, your favorite network and system attacker/protector. If no one else loves you, Hank loves you. Love, peace, and chicken grease, and I will see you in the next video later.